Today we are going to be talking about 3D graphics. More specifically, how we can create 3D graphics using math. One thing many people don't consider when they look at 3D images on their screen is how those images are actually created. Luckily, with orthographic projection, we can create the illusion of 3D graphics while using 2D images. To visualize this for you, we'll be using a tool called ShaderToy, which compiles OpenGL shading language code in the browser.
In a 2D display, like the one provided in ShaderToy or on the screen, each pixel's location on the screen is represented as a 2D component vector with the pixel's x-coordinate and y-coordinate. For a circle to be drawn onto the screen, we can define a center point and a radius to compare to. Then, for each pixel on the screen, we can calculate the distance between said pixel and the center using the Pythagorean equation. If the distance is less than or equal to the radius we defined, then we can return a 3-component vector that represents the pixel's RGB color values. In our case, white is a vector with 3 ones, and black is a vector with 3 zeros. Finally, our program looks at each pixel's location vector and sets the pixel's color to the RGB value we defined, making all pixels within the radius of the circle white, and all others outside black.
Things get more tricky when you move from 2D to 3D because you have to translate from the third dimension down to the second. In 3D graphics, there are two main ways of representing a 3D space on a 2D screen. The first and simplest method is called orthographic projection. An orthographic projection takes a point in a space Rn and represents it in a subspace W of Rn using an orthogonal vector, which is a vector that is perpendicular to all the vectors in the basis for W. An easier way to imagine this is by taking a point in 3D space and mapping it to the closest point on a 2D plane. Simply put, orthographic projection treats each pixel on the screen like a little camera in a virtual world. Each pixel shoots a vector straight ahead until it finds something in front of it, then changes its color to match what it is looking at. Orthographic projection results in a flat-looking representation of a 3D space, because it has no way to represent depth. Faraway objects will look just as large as nearby objects. To provide the illusion of depth, we can use an alternative method called perspective projection. To use perspective projection, instead of treating each pixel like its own camera, we can have a singular camera that sits behind the center of our screen and shoots vectors through each pixel on the screen. As these vectors proceed out from the screen, they get further apart, which means things that are further away will be hit by fewer vectors and consequently appear smaller on our 2D screen.
In order to implement perspective projection, we need a way for the computer to know what the objects in our 3D space look like so that it can detect when a vector hits an object. A popular technique for detecting vector collisions is Raymarching. With this technique, we start at our camera point and follow a vector through each pixel on the screen. From the screen, we find the shortest distance to an object in our scene. Once we've found that distance, we move along our vector by that amount. We repeat this process until our vector touches an object or until it extends too far into the distance. Here's a visualization of Raymarching. In this scene, we have a camera, a screen, and 2 spheres. Let's send out a vector from the camera through the center of the screen. Next, we find the closest object, store the distance, and march our vector forward by that amount, keeping the direction of our vector. In this case, the sphere on the left is closest to our current position, so we'll find our distance to the sphere and move forward by that amount. Eventually, this process makes our vector collide with the sphere on the right, so we can tell the computer to stop marching and return a color value to represent that sphere on the screen.
Let's use Raymarching to display a sphere on top of a plane in ShaderToy. First, we'll need to make a function that finds the distance from a point to the closest object in our scene. In this case, we just need to compare the distance to the plane and the distance to the sphere. We can get our distance to the sphere by finding the distance to the sphere's center minus the sphere's radius. Meanwhile, if our plane is all the points with a y-coordinate of 0, the distance to the plane is just a point's y-coordinate. Next, we'll make a Raymarch function that repeatedly moves a point along a direction vector by the result of the distance function. If the point touches an object or goes too far from the camera, we stop marching and return the distance we have marched. With these functions, we can begin the Raymarching process. For each pixel on the screen, we define a vector that starts at the origin point and points towards the pixel's x and y coordinate on a screen in front of the origin. For each vector, we perform a march. If we set the brightness of each pixel to the length of the marched vector, we can make closer objects brighter and further objects darker. The end result is a sphere on top of a plane with a dark fog around everything. There it is. We have just used Raymarching to perform a perspective projection of a sphere and a plane in 3D space on a 2D screen.
To give a quick review, there are several difficulties that can be found in representing a 3D object in a 2D space. Thankfully, we can use math to circumvent most of these, using a variety of methods. The first being orthographic projection, in which you map 3D points onto a 2D plane by finding the closest point from the 3D point to the 2D plane. You can furthermore use Raymarching to represent 3D spaces. Raymarching is a technique used to detect vector collisions. Essentially, you use this method to trace a path of vectors until you collide with an object in your 3D space. We visualize these methods for you in ShaderToy by making a 3D sphere for you to view. While we've given you an introduction to 3D graphics, there are a number of other ways to represent them using math. Here's some of the code we've used in this demonstration. Other sources we used will be linked in the description. Thanks for watching, and feel free to ask any questions you may have.
Whoa! Eat it, eggheads! Class is dismissed! Whoa! Whoa!